When I came to TIFR, I changed my research area, and I should say that I was highly influenced by Deepak to do statistical mechanics, and after that I've been continuing in doing statistical mechanics, and I actually learned a lot from both Deepak and Mustansir while I was in TIFR, and that is what is giving me whatever I have been doing, over years. So thank you, Deepak and Mustansir, for shaping the understanding of what we have in statistical mechanics. Not only me, many people, many of our students and postdocs probably appreciate that. So with my talk, so what I'm going to talk today is non-unique steady states. Okay. So usually non-equilibrium and equilibrium systems are modeled by Markov chains. We have a master equation, and in the master equation, the off-diagonal element Mij just tells you that the rate of going from J to I, configuration J to configuration I, and in the diagonal you have the out rates from configuration I. It's a sum over J I to all other configurations. That's the master equation. And what you have is that eigenvalue. You have eigenvalue equation M psi k equal to lambda k psi k. That's the eigenvalue equation. And just because the determinant of M is 0, you have a stationary state, what you call the steady state. And if the state space, the configuration space is ergodic, which means that you can, starting from any configuration, you can go to any other configuration, then M corresponding this matrix M is irreducible. Okay. So this actually says that there is a unique stationary state, because if you have a positive, because these are rates and these are positive, and if you have a positive irreducible matrix, then Perron-Flovenus theorem says that the largest eigenvalue of that matrix, which is in this case 0, is unique, and its eigenvectors, the components of the eigenvectors, are also non-zero, strictly non-zero. Okay, that necessarily says that for every configuration there is some finite non-zero probability, and that is unique. Okay, so the system, so if you talk of systems with observing configurations, which means that there are configurations which are connected, but there is one configuration, let us say one observing configuration, which means if you can go there, you cannot leave. Okay, you permanently stay there. So if you have a situation like that, your master, this Markov matrix corresponding M matrix, so that will look like this. This is just one. This is the observing configuration in the basis. Observing configuration is the first one. So you have incoming rates, which is sitting here, called V, and you don't have any outgoing rates, which means all these are zeros, and the sum is also 0. So these red ones are 0. Okay. So the matrix is in the form 0 sum V, 0 D, and this is certainly reducible. Okay. So you can say that the stationary state in this case is not protected by Perron-Flovenus theorem, but you can see that the eigenvalues of this equation is just 0, which is just 0, and all the eigenvalues of D. Okay, so this, and 1 0 is a simple eigenvector of this, which means that this is the actual stationary state of this problem is just 1 0. Okay, which means that you certainly go to the observing, starting from whatever configuration, in t goes to infinity, you will be absorbed. That is the situation, and that is not very interesting. So what you look for is that the next eigenvector corresponding to the next largest eigenvalue, which is the quasi-stationary state in this case. Okay, we will see this. And in the quasi-stationary state, what happens is that if you, for example, if you take an example of directed percolation, and if you take different system size for a given system size, starting from any density, the density goes down, and for a small system size, it drops to 0. It is absorbed at some time t, and if it is a larger system size, it absorbed at a different time t. So when t goes to so L goes to infinity before t goes to infinity, so in this situation you have a stationary value. Okay, so that is what you call the stationary t, and the stationary state in this case is unique because D, this matrix D, this is also irreducible. Okay, which is fully connected. So what we are going to take is that, if you have pair contact process, then you have many observing configuration. Starting from a configuration, you might go to any of these observing configurations. It will look like as if it is non-unique, but that is not true. the stationary state is not the question. The question is in the second largest eigenvalue, which is still unique. Okay, so in this situation, this is still unique for pair contact process, directed percolation, and this is still unique. Okay, question is that at what we're going to ask now, that at what situation you can get a non-unique stationary state or quasi-stationary state. Okay, so if the system is non-unique, then so if you have you calculate the transition from J to I. If you start from a configuration J, what is the probability that system survives in the configuration I, that is QIJ. Okay? So that is just, you start from I, evolve it to this Markov matrix, and then you take this one, and then you want I which is not 0, so k not equal to 0, and you sum over this. This is just this is the surviving probability that you are not in absorbing. This is the total survival probability. Okay. Now, if you decompose it in the so if you decompose it in the eigenspectrum of M, then this will look like psi. You just insert it here, and you can see that psi ni just gives you, t goes to infinity. This psi n will just replace by psi 1. Okay, because that is the largest eigenvalue here. So this will just e to the power lambda 1t, and here also you get e to the power lambda 1t. This sum goes, only one term dominates. So this just goes away, and this becomes independent of this becomes independent. So this is a mistake here. This is I1. So this is just I. It is independent of J. Okay. So the question is, can stationary state be non-unique? And the answer which I'm going to do here is yes. If the stationary state can be non-unique, quasi-stationary state can be non-unique. And we find some interesting example and a criteria when stationary state can be non-unique. So we start with an example. So let us say that there is a system which is a conserved dynamics. It could be safe, or it is Kawasaki dynamics of Ising model. Some kind of conserving dynamics is going on. Actual dynamics doesn't matter for our purpose here, but we'll give an example of safe. Okay. So if you deposit a particle, the rate depends on the local coordination number here, where you are depositing, how many particles are there. The rate depends on that. And this local coordination depends on the total density, average density of the system, rho. So the density, the deposition rate, or the birth rate, and the death rate, both are rho dependent, density dependent. We take this as this into the account. Okay. So deposition rate and death rate, birth and death, both depends on rho. And on the top of it, we set B of 0 equal to 0. So birth at 0 equal to 0, which makes a absorbing state, which means that once you go to rho equal to 0, then you cannot create particles anymore. Okay. So rho equal to 0 is absorbing configuration. Okay. So now the question is that, do you have an active absorbing phase transition in this place? In this situation, we take a very specific example. So the dynamics again is that 0 going to 1 with B rho, this is the rate. 1 going to 0 is D rho, this is the instantaneous density. And diffusion, of course, is there with rate 1. Okay. So along with that, we also say that the birth and death, these rates are extremely slow, which is e to the power minus L times some function. And this is incidentally, we choose it. There can be many other functions. Okay. So, which is minimum, one minimum. So D rho and B rho is chosen like that. There is a rho sitting here, which means that B 0 equal to 0. So in this situation, just shape and birth death with density dependent birth rate, this is the rates. In this situation, we have an active absorbing phase transition, which is given by this diagram, which you see here. So what does it mean? Let us say that you say that there is a parameter here, like 2 divided by B. This is a birth parameter, and there is a D here. So this is a death parameter. These are same functions, so written little differently. Okay. So now if you put B equal to 0.5, B equal to half, and you go along this line, change D, then what you see is that at this set you have 0, and as soon as D become positive, then you have the density of the system becomes D. Okay. So the density changes, starts from 0, and it goes all through to 1 here, and it remains 1 here. So this is after that it remains 1 here. Okay. After D equal to 1, it remains 1. Now, if it is at 1.5, the density goes to 0, and then it becomes D. And at this point, there is a jump. It goes up to D, and then suddenly it jumps to 1. Okay. So there is a second second discontinuous transition here. So this discontinuous line ending with a tricritical point. So you can see that there is a rich variety of phase diagram. You get a rich variety of phases here, but this red line is the absorbing transition line. So D equal to 0 is the critical point of this phase transition. It's a very simple one. So the idea is to see if there is a non-unique stationary state in this situation. Okay. So how to understand this picture? This phase transition is that you have a first you notice that there is a separation of time scale. Okay. So birth and death rates are e to the power minus L something, which is extremely slow. So which means that between two consecutive birth or death processes, the system has enough time to equilibrate. Okay. So you can think this is a quasi-static or well-stirred condition. Okay. So you have enough time to equilibrate in between, which is because of separation of time scales. And the effective dynamics of the system can be thought as if it is a random walk on a L+1 lattice sites with an absorbing boundary at 0. And
Hi, Professor. You have 2 more minutes.
Yes, okay. So the rates are given by 1 minus rho and rho d rho. Okay? So these are the rates, which are modified rates. So effective dynamics is this, and in this situation, when the birth is greater than death, the system actually goes to rho equal to 1, and it will. But otherwise, if birth is smaller, then the BD less than 1. That is the condition. In this condition, the system drifts towards rho equal to 0. Most of the time, system is absorbed, but those who survive, they will survive wherever the rate is small. The out rate is small. Out rate from the system is slow. Okay, so at that density, the system waits very long time, and that is the meaning of minimum of Bn plus Dn, which is rho s equal to D. Okay, so that is the way you get all this phase diagram. It can be explained using the Landau phase diagram also. I'm not going to explain. But the interesting part is that when you take B equal to 0, the birth doesn't happen in this situation. What you have is that you have a phase transition at D equal to 0, but that depends on the initial condition. So if you have an initial density rho 0, which is distributed by 1 plus n rho to the power n, which is normalized, then n equal to 1, n equal to 2, n equal to 3, the densities will be different. Okay, so at this stage, you have, if you define the critical exponent beta equal to 1, whereas gamma, which is the density fluctuations, that will be gamma equal to n plus 3. Okay, so this is what happens. So the point which I want to say is that why this non-unique stationary state occurs. We have a very nice mathematical explanation, but I don't think I will be able to tell you here. But what you can say is that the master equation, when you write the master equation in this basis, where M0, M1, and M2 are the matrices in the M1 is CL1 dimensional, this is CL2, this is the dimension. So if you do this, you can find that the corresponding the largest eigenvector, the quasi-stationary state, has 0 components somewhere, which means that these components are 0. So you have this is 0, this part is 0, this part is 0. So if you start somewhere here, the system will come to rho equal to rho star. But if you start somewhere below, then it will be distributed somewhere here, because because there is no birth, the system is going always towards this. So there is a density distribution here depending on the initial conditions where you start. Okay, so that's what happens. So we can ask a general question: what system can exhibit non-unique stationary state? Okay, so the answer to this question is the system which has more than one open communicating class. Okay, so let me define what is a communicating class. All the configurations which can be reached starting from one to the other, starting from any configuration, so they form a communicating class. So in this situation, this is the whole phase diagram. In this situation, there are 3 communicating classes, because these green ones can go from one to other, but from green to violet, if you go, then you cannot come back. So there are 2 different communicating classes. These are a communicating classes is called closed if it is impossible to leave once you go there. So A is a closed communicating class, and all other communicating classes are open. Okay. So what happens? What happens in systems like directed percolation, compact process, restricted exclusion process, or assisted exclusion process, or the problem here with SAP plus birth and death, all of them has only one communicating class, one open communicating class, and there is one absorbing configuration. Okay, so what happens is that you go from all the time you just move around here, which is connected, And once the observing configuration is gone, you have still like one connected space. So you have a unique stationary state. Similarly for PCP, because you have all of them, but if you drop all these observing configuration, you have still a connected space, fully connected space. But that is not true when safe with a birth, because if you start with L equal to rho equal to 1, then you can go to N equal to L minus 1 like that. But once you go, you cannot come back. Okay, so that makes SEP plus death has L open communicating classes that makes non-unique. This gives a possibility of a non-unique stationary state. Okay, so this kind of open communicating class necessarily tells you the corresponding Markov matrix is irreducible. You can see that M1, M2, M3, there is nothing below diagonal. This is not fully, not off diagonal, because these matrices has non-zero element below diagonal. If you write it in this basis, then only it becomes looks like that. So this is still reducible in this way if you write. Okay, so that's what I stop saying, that system which is more than one communicating class it can exhibit non-unique stationary states. I stop here. This work is done with one BSMA student, Karthik, and he has Okay.
Thank you for this. Yeah, thank you for this interesting talk. Okay, so there are not a raised hands and no questions in the chat box. So thanks a lot, Professor, for your
Yeah.
somebody.
I wanted to know if just the existence of transient states is the same as what you are discussing as multiple communicating closed classes.
Okay.
If you have like the first set you showed is a transient set of states.
Yes.
So is it enough to have some transient states? Then you will have multiple closed sets.
Yes, I think that is true. Yes.
Okay, thank you.
So, are there other questions? All right. So, thank you, Professor, for this interesting talk.